Okay. Good evening, everyone. Welcome to the Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Alexandre Reiffers. He will be speaking on what can be recovered under sparse adversarial corruption, assumption-free theory for linear measurements. Professor Alex has developed a research trajectory grounded in applied mathematics, optimization, and learning, with a strong connection to the real-world systems and industrial applications. After completing his PhD at INRIA on game theoretic models applied to online social networks, he worked as a research engineer at Saffron Tech, where he studied predictive maintenance policy strategies using stochastic models and reliability theory. From 2018 to 2020, he pursued a postdoctoral position at IISc Bangalore, India, focusing on information design and decision making in IoT and industrial systems. Since joining IMT Atlantique as associate professor in March 2020, his research has focused on adversarial learning and distributed learning for network robustness, fault detection using machine learning, stochastic processes for distributed ledgers, and stochastic optimization problems for resource allocation problems in cloud, defense, and cybersecurity. He is also coordinator of 2 international projects that bridge AI and distributed systems and security. Also, apart from all this, he is also a fitness enthusiast. Earlier, he gave me some fitness, the running suggestions and all, so please feel free to talk with them after that. Yes, that's true.
So thank you for the kind introduction. So this work was a long pending question that Gohan and I were asking ourselves since 3-4 years, and most of the work has been done by the PhD student, Vishal Adler, who was there in ISC before. He was a master student, so some of you know him. And so I will basically present his work. Okay. So in many systems, measurements can be corrupted by a small number of malicious or faulty sensors. And so always the question is how to model that and what can recover in such setup, right? And classical example is in network monitoring, where you are trying to recover the routes in a network and some of your routers are compromised. I'm not saying how it can be compromised, I'm just saying that they are faulty in some sense. And it can be adversarial or not. Then in power grid, you can attack directly the smart meters, and this is actually, with all the wars that is happening in Ukraine and so on, this is actually a pretty realistic scenario. In distributed sensing, sensors are hijacked, and also in medical imaging, you can have sparse artifacts called outliers and even adversarial perturbation. And you know, if you really want to ask yourself what can be recovered, you have to start with the simplest model possible, otherwise most of the results have to be done through experimental results. So let's say that you have a linear model, y is equal to a of x, but what your nose is sparse, right? So basically you have some of the line, some of your sensors that are corrupted. So what is known in this problem is that your measurement matrix A is known, your observation also, but what you don't know is your signal and where is the corruption. The only constraint that you put is the fact that it's sparse. So let's just discuss about why this model is quite standard, except if you remove the Gaussian noise. Most of the applications that I've described can be up to a certain level of linearization, can be represented as this model. And because the theories that we have built there is the first of its own, we are obliged to start somewhere. So we start with a linear model. Okay? So the classical question that people have been asking themselves in such setting, right? It's exactly the same setting, and it started with Tao in 2008, was can we recover X? And what are the conditions on A such that you can recover X? And how? So this is the entire literature of compressed sensing is basically working on this problem, right? But we even question whether or not this question is a good one or not. Because actually, when you look at condition to be able to exactly recover X, it means that you have a lot of redundancy in your measurement, right? So if you think of, you want to be robust at this type of noise, then you need to measure a lot of times the same thing. Why so? Because most of you, I guess, are used to having this noise bounded, but not in norm 0. When it's in norm 2, for example, it means that your energy is bounded. Implicitly, it means that the variance is bounded. But here, I'm not saying anything about how the measurement can be. It can go to minus infinity or plus infinity, but just on a just on a small number of sensors. So this is why it's actually so hard to recover them. And this is why we call it adversarial also, because the fact that you don't know E, of course, it's not just an adversarial, it just can be a sensor that is failing, but you don't want to put any statistical model on it. So this is why we took this model. So what is the right question then? So the problem is, if you don't put any assumption on A, the adversary can choose the worst possible entries, right, according to my assumptions. And corruption can mimic another signals. So it's extremely easy to design two signals x1 and x2 such that your measurement is the same and you have the same level of sparsity. I hope that you are convinced by that. So basically, recovering x star is fundamentally impossible for most A, right? And we will dig up a bit more in this question.
Two distinct, like suppose x1 and x2 are, let's just say suppose everything is binary and A is identity, and x1 and x2 are say Hamming distance larger than q.
Why you are talking about Hamming distance? I'm talking about right now we are working in real numbers. So why Hamming distance?
Okay, so like the number of positions that are different, x1 and x2. Suppose that is larger than q. Then I can take it. I mean, okay, I'm just throwing some very.
So perhaps I think it's good that you are trying to understand the problem on your own. So I think let me continue, and perhaps you can refine your question after, if you don't mind. Okay. So the right question for us was not can we recover everything, but rather what can we guarantee to recover, right? And more specifically, because it's a really general question, right, and it's not really well defined, we focus on a specific way of what we want to retrieve, and something that is in some sense interpretable is which component or linear combination of x star are invariant to any k corruptions. Okay? So I will just give you the main result right now, just to show what we can recover, and we have shown that it is actually the best thing, and then I will try to give you an intuition of why it is the right result. So the recoverable information forms a linear subspace of this form, right, where basically it's just a subspace common to all the row span of all the matrix generated in the following way. You take the matrix A, you remove 2q rows, right, and then you look at the common row space. Okay. So what is interesting there is that this 2q, it's not so tricky. You will see when I will give you the example why it's 2q, but you know, initially when you think of this problem, you will be more convinced that it will be q, actually, and not 2q. And then the interesting things that we can prove is that there is nothing more that can be robustly recovered, right? So basically, everything is captured by this space. Okay? So for sure, there is some link in coding theory, but we have not yet, you know, means that we have tried a bit, but we are not we are not coding theories. So on finite alphabet, we didn't try. Okay? But yeah, fair enough. This 2q is actually, you can have an interpretation, but whether or not it's useful is something else. Okay? So now let's look at. I don't know. This actually, I'm a continuous guy, you know, so I actually have no clue at all. It means that the recovery question has been, full recovery has been solved, right? But what can be recovered? And usually, if I'm not wrong in coding, your goal is actually to fully recover stuff, right? To create codes that can be recovered. So I don't have an answer to. Sorry for that. So let's say U is the orthogonal projection on a projector into this robust subspace, okay? So now, imagine that we're able to compute U, right? What can we say is that for any two visible signal x1 and x2, such that you have an equality in your observation, then you necessarily have u of x1 is equal to u of x2. So this is kind of the interpretation and how it can be used. So basically, u of x star is in this case a maximally recoverable information, and the kernel of this matrix U represents basically the ambiguous direction where you cannot distinguish signals. And depending on the applications that you are studying, and I will show one of them, it's really nice to observe what is actually U. Okay? So let's look at this simple example. So this is your observation matrix, right? So you have to imagine that the line represents a sensor, and what do you observe is that the line 2 and the line 5 are the same, the row 1 and the row 5 are the same, and the row 1 and the row 2 are also the same, and then it's a linear combination. So basically, you observe twice the same thing, right? And you observe something, a linear combination of the two. Okay, and let's say that you have one row that is corrupted, so one sensor is corrupted, but you don't know how. So what can be recovered, right? So clearly, first of all, in this matrix, even without corruption, you first can observe that it's not possible to recover X, right? So my question is, imagine that you don't have corruption. What can you recover when your matrix is not full rank? Does someone know the answer? So basically, X plus the kernel of A. This is what you can recover. Okay, so we are trying to build something like that, a representation of what you can recover in terms of kernel, the ambiguity direction, but with adversaries, right? So what you can recover there is, imagine that I'm deleting this line, okay? Then you can see that you can still recover x1 plus x2 plus x3, and you can still recover x4 plus x5, right? And you do that with every line, you see that you can recover. But what is tricky is that so at least you should be able to recover that, right? It's just a constant, yeah. But it's even more trickier than that, because right now I told you, imagine that I remove this line, then I can recover. What would be a naive algorithm in this case to check what I can recover? If I'm really stupid, what I will do is I will just use a voting algorithm, right? So I will suppress a line, I will check what I can recover, I will suppress another line, I will check what I recover, and so on and so forth. And then I will kind of do a vote among everything and see what is the common things that I can recover in every case, right? This is kind of a really stupid and heavy procedure, but this is what you could do, right? So imagine that let's assume that the first line is corrupted. Then what can you recover? X plus kernel of this submatrix. Then, yeah. Yeah. Then what you can recover if I remove this one is X plus the kernel of the matrix A when I suppress the second line. And I can do that with all the line, right? So it's creating a set of subspace that I can recover. And then because you don't know where is your adversary, you will look at the intersection to check what is the thing that for sure I can recover no matter what.
So just take this example. If I have, let's say, I do not know what it means, right?
You don't know. You never know.
X1 plus X2 plus X3 plus E1.
Yeah.
X4 plus X5 plus
yeah.
E2 and so on and so forth. And then what are you saying? So now, what do you mean by majority, right? So because these are different.
There is no majority. It's not a vote. Sorry, it's an intersection. You look at the minimal things that you can recover.
So what is intersection here I can get? So because you do not know E is there, right?
You don't know, but you will create a set of space, right? A set of sets that could be recovered, and then you look at the intersection.
I mean, using your theory.
No, just what I just said.
No, you suppress one.
You suppress one, you look at what you can recover, what is possible to recover. So basically, it's controlled by the kernel of this submatrix. Exactly. And you do that with all. Okay? So this is still doable when you have one adversary, right? But imagine that you have Q adversary. Yes, please.
So this might be a very basic question, but
Hmm.
so since A is not full rank,
Yeah.
how can you get X star?
You will never get X star.
So even without noise, so what?
This is what I said
I
just
know,
before.
yeah. So what's going on? So why are you looking at this matrix in the first place?
Because a lot of applications actually are never full rank.
Okay. So we can never hope to recover X star exactly.
No, but you can recover subspace.
Subspace, yes.
Okay.
Yes,
And the question is, imagine that if it's even more corrupted,
okay.
you know? And then I will even ask another question. Imagine I design a full rank matrix, okay?
Okay.
If I attack it, it's not full rank anymore. So still the question is pertinent. You see, it's not because you have a full rank matrix that you know that you can recover with adversaries. You did extra conditions. So our theory is there to kind of push the limit. You know, people always ask themselves, basically, what is the amount of redundancy that you need to have in measurement to be able to have recovery? My question is, you give me something, I will tell you what can be recovered or not. Okay? So the question is, how do we formalize a bit more the intuitions that I gave, right? So what you notice is that the row span of A is just the span, yeah.
So it's still sort of clear. If you give me Q, right, then I will remove a Q subset of
Yeah.
the rows, right, and then I'll look at the rest and
Yeah.
look at what is span, right?
Exactly.
And the same idea as what you said.
Exactly. So this is giving you the intuition of what could be recovered,
Right.
right? We have also shown that it's kind of the best thing. Okay? So if we go back just to finish my example on this matrix, right? So the row span of this matrix is just composed of these two vectors, right? I hope that for everyone it's good. And you see that every time you remove one line, right, in all the combination, first of all, you never perturbate this row space. This row space is the same. And if you remove two lines, because remember my condition is with 2Q, you still always have the same row span. So the only thing that you can recover is basically belonging to the span of U and V. Okay? So in some sense, even if this matrix is low rank, it's kind of robust because you preserve with one adversary the span of the matrix, even if one sensor is attacked. Okay.
Yeah, you have some intersection of subspaces.
Yeah.
So how do you choose your one X star, like
Really
L1
good.
norm, L2 norm, whatever?
At the end of the talk, I will tell you. Really good. So now we have to define a bit more precise. I will try to give you intuition of why the 2Q, right? So we will define what is called an ambiguity set, basically where we are not able to distinguish measurement. So let's say, I will start with the example. Let's say that you have this matrix A, and you have two attacks possible, right, of the same level of sparsity, 1, and you have two different X, and you see that it's giving you the same measurement, right? So it means that you see that it's possible to not be able to distinguish X, right? And also it's not able to, and also the attack is not at the same place and will produce two measurements. And this is where the 2Q is appearing in our model, because when basically you want to be able to compare stuff, right? And to be able to compare stuff, but attack can be at two different places, right? And this is why you have the 2Q. And what you see clearly is that X1 and X2 are not indistinguishable to the observer, and it's equivalent to say that in this case, X1 minus X2 is belonging to this set. And you know, a simple computation, because if this is equal to this, so you will have a subtraction just between the noise vector, and you will have this 2Q. And you can prove that it's equivalent. Okay? So now you didn't get 2Q. So do you agree that these two signals are equivalent? These two observations are giving you the same thing. What is tricky is look at the attack. It's not on the same sensor. So when you want to compare two measurements, you have also to check. Your goal is not just to retrieve, right? Because you are doing, this is the problem with an intersection. You will have to compare elements with each other.
So what is clear is that E1 minus E0 zero norm can be to third is clear.
So this is what is called the ambiguity set. Is you take all your v in this direction, you will never be able to recover them. Okay? And you know all the theory of compressed sensing and the paper and the work of Digavy and so on, when they think of full recovery, implicitly they try to say that they have A such that this is empty, to not have ambiguity direction. Okay? Okay, so now the question is, we have to define what is robust. I'm talking about robust subspace, but it's not clear at all what it is, right? For now, what you would understand is robust decoder or measurement. But let's try to see what is something robust. So let's say that you have a matrix A, and you have a certain level of attack, and you have a function phi, which is, let's say, AQ robust. And we say that it is AQ robust if the moment your measurements are equal, then the function is equal for the same x1 and x2. Okay? So this one is kind of hard to interpret, but let's just imagine that phi is a linear function. No, g is a linear function. Then you see that it just means that you are living in the same space, right? You will have u of x1 is equal to u of x2. Right? Just think of this linear example. And what is a robust solution set for a function phi? It's the set of x where all your functions are equivalent, basically. D'accord? So let's see the main theorem of the paper. So as I said, the moment you construct this linear space, right, and you take u as the orthogonal projector into R, then you have the following. The map u of x is AQ robust, so it means that you can recover u of x, right? You cannot recover x, but you can recover u of x. So I gave kind of a constructive way to find basically the orthogonal projector of this space. And the other thing is among all the solution map that you have, right, that can be recoverable, because I hope that you agree that u of x is a map that can be recovered, but you can have any nonlinear transformation, right? We could try any other stuff that could be robust, but we focused on linear for two reasons, because it's the one that is interpretable for us. And the other reason, it's because it has a nice property, it is the smallest one in terms of set. So every other function nonlinear that you would try to recover would be something more complicated and will give a bigger set of solutions. So this is the minimal one. Null space. Null space. Okay? So basically, the inclusion-wise minimal solution set that is robust to Q adversarial corruption is x star plus kernel of U. Okay? So it's really nice. We have a full characterization of what can be recovered. Bon, you will tell me, thank you so much. First of all, how to compute that and how to get x star plus kernel of U. Okay? So this is where comes a second simple result. Let's say that you are solving simply the L0 regression, y minus a of x, right? Then you know that any solution of the L0 solution will satisfy u of x hat equal u of x star, where x hat is the L0 regression. And therefore, for the u that I have defined before, because the orthogonal projection on calligraphic R. So now we have a way of exactly compute the entire information that can be recovered for A, X, and some measurement Y. So the algorithm is pretty simple. Compute X hat, right, using the L0 decoder. This, there is available algorithm. Of course, L0 is hard, but there is some good algorithm to do that. Compute U. I will tell later how to compute U. I will at least give you some hint. And then return k hat plus kernel of U. And this is giving you the entire set of solutions that can be recovered. Okay? So the algorithm I didn't put the algorithm because it's kind of really combinatorial. Really, the algorithm is try to compute the orthogonal projection of rho of AT. So basically, it's basically what you do is you compute a basis for the kernel space of all the AT a bit smartly. Then you aggregate that in a big matrix, and then you compute the image space, and that's it. So, okay. So the problem is this algorithm is exponential in the size of the matrix, N, right? And also, we have been able to prove that actually it's an NPR problem. Okay? Okay. Okay, so is it finished, the story? Not exactly. Before even given more theoretical results, let's see why it's useful, right? Because it's nice to do all this math, but it would be nice on an application to see why it's useful, what is the shape of U, and so on and so forth. So actually, this problem came from a network tomography problem. So for the people that don't know network tomography, it's a simple problem. You have some link metrics, let's say some delay on links on a graph, and you have some path measurement, and you assume that when you go from, when you take a path, you will experience, for example, a delay, and the delay is the sum on all the metric on the path. Okay, so this is a classical network tomography problem. And you assume that some of the measurements are corrupted. So for the people that do a bit of networking and have tried to do some path measurement on internet, clearly you see that this makes sense. Because most of the time, when you do some ping, you don't have answers, and you are not able to have correct delay, and the round trip delay is hard to measure, and things like that. So actually, imagine that some of the delay are corrupted, right? Some of the paths are corrupted, and the question is, what can you recover, right? So this is my routing matrix. So I have 1, 2, 3. Bon, I have a lot of paths, right? And I will ask myself, what can I recover at the level of link? Can I, for example, why it could be important, imagine that one of the link is failing, so I have high delay. Am I able to identify or not this link? Okay. So you have your matrix A, which is basically the path link matrix, and you will compute U. And once you compute U, you will get the following information. The image of U will give you the robust subspace of link quantity, what you can learn. The basis vector will tell you, we kind of show you exactly on the graph what can be learned, and then we can also derive kind of a robustness score. And the question here is basically which link can be always recovered in this case when you have k corrupted paths. Okay. So in this example, this is my U matrix, and let's observe this matrix. You have one corruption. Okay. We don't know where, but only one path is corrupted. So you see that you have a lot of lines to 0. Sorry, a lot of rows to 0, and you only have this column where you have only a 1, then this one, and this one. Okay. And we know that this is the best thing that you can recover. So now let's try to visualize it. When you look at the basis vector of this matrix U, right, you see that you can recover exactly what's happening between 0 and 2, exactly what's happening between 4 and 3, and then a linear combination of what's happening between 6 and 4 and 3 and 2. So this is really fascinating in this case because it's kind of giving you exactly what you will exactly be able to measure when you have one attack. Okay. And if you don't, and if you have more than one attack, in this example, you cannot recover anything. Okay. So what this subspace is telling us, so there is only 3-dimensional subspace that can be recovered by looking at the rank. And then exactly what I say, you can exactly measure no matter what x3 and x5, and you can only say something about x4 plus x6 plus x7. And the rest you cannot guarantee anything. Okay? Also, what is interesting is that you can define a robustness score, and I will explain why it's important in network tomography. If you just look at the diagonal, if of your matrix U, if Ujj is equal to 1, it means that you can directly recover the link J. If it's equal to 0, it means that you never can say anything about it. You don't even know to which set it's belonging to, right? And then, if it's between 0 and 1, it means that link J participates in the robust linear combination. And why this is really important, there is something in networking called topology of obfuscation. And the goal is, imagine that you have a network, and you are the owner of the network. And let's say that this part is really important for you, right? For some reason, this is really crucial that this is where, if, for example, you shut down node 4, you are not able to, you lose connectivity and things like that. And people have asked themselves the following question, is as a defender, how to corrupt the measurement seen from outside such that people are not able to recover the topology, and even more precisely, are not able to recover the crucial nodes. And these tools can be used to do that, because by playing with the adversary and what the guy is saying, we can kind of see what is exactly be able to estimate and not, and we can try to modify his measurement. So in this case, the A matrix, such that it's not able to fully recover the topology. So it's an important problem in networking and in cybersecurity. Okay? So this is just an example to show you that it's actually useful for certain problems. And now we will do another example to kind of go a bit more, try to challenge a bit our question and ask ourselves, but is it really interesting to check whether or not something is robust or not? So what we have done is we have built a matrix A by sampling from a DCT matrix. So it's just such that in DCT matrix, all the columns are orthogonal. So what you want is you can sample them multiple times, and you know that when you sample a line, except the lines that have exactly the same row, except the rows that have exactly the same values, the other one will not bring any more information. Okay? So basically in this case, because the rows are orthonormal, so the robust direction corresponds to the rows that appears a certain number of times in A, and you know that you are robust, a row is robust if it's appearing 2Q time for Q adversary. So this is my theorem there, because everything is independent actually. Okay? So now it's really easy in this case to compute the subspace. You just need to count. How many times I'm seeing this row, how many times I'm seeing this row, how many times I'm seeing this row, and I'm putting a threshold, right? And if you look at this matrix where we have 500 rows, you see that even with one adversaries, right? Even with one adversaries, only 2 rows can be fully recovered, okay? And it's even worse. So we have tried something much bigger, right? So no, not much bigger, but what we see there is that the number of adversary is going up to 8, but you see that it's really decreasing really fast the size of the subspace that you can estimate. And it's actually really interesting because it's kind of going a bit at the opposite of saying that the problem is NP-hard. Because mainly the problem is NP-hard when you have a lot of adversaries, right? But what we are saying is in a lot of numerical experiment, we see that we don't need so many adversaries, perhaps 3, 4, 5, and at some point you just get always the empty space. It means that you cannot recover. So Q, the number of adversaries, doesn't need to go too high to get an empty space. So it's going a bit against this NP-hard intuition because you don't have so much complexity at the end. You don't need to look for so much adversary. Why? Because the adversary is all powerful. This is because it's a worst case scenario, so this is why. And what we have tried to do, so as I said, as Q increases the number of robust, basically the rank of your robust matrix drop sharply. And that when you have 8 adversary, even in a matrix of size 500, only one atom remains robust. And so basically here, the intuition is that uniform sampling creates many low multiplicity atoms, and the sparse adversary can erase them by corrupting only a tiny fraction of measurement. Okay? So we'll try to get a bit into this intuition a bit more. And this is a recent result that Vishal has produced. So imagine that you have a matrix A where the entries are drawn with ID standard normal entries, right? What he has been able to prove is that when Q is smaller than m minus 2 divided by 2, then with probability 1, the subspace, subspace is the entire space. But when the number of adversary is greater than m minus 2 divided by 2, then you cannot recover anything. So this is really impressive because it's kind of killing the purpose in our theory in this case. The theory would be more to say, can we recover, at least in this case, can we recover something or nothing? It's still a really hard question, but it's much more simpler than everything that we have done. Yeah.
In previous case, when you considered DCT, you
Yeah.
mentioned that when you uniformly sampling, there are no repetitive columns. Rows. No repetitive rows.
No, you repeat them. It's sample with
No,
replacement.
the number of multiplicities are very small.
Ah,
Because of
yeah.
that,
Yeah.
you are not able to recover. But
Yeah.
whereas, if you consider in A,
Oh.
if you take any two rows, them being exactly the same is also pretty small. So why in this case you have this phase transition kind of behavior?
So it's a result that appeared last week, so I don't have interpretation. So I just wanted to tease you. So this one is extremely interesting. I actually don't know. You know, it was already a lot of stuff before, and this one, I don't have any clue. And I don't want to. Huh. Mm.
Space conditions appear when you go to this large particle
Yeah.
system, right?
Yeah.
So this is just
This is, but to check. Huh? Let's put it that way, is I should say to check. All this, I have to be careful with this, but at least it's coming up with the intuition that if you don't really force the redundancy, most of the time it's easy to kill and to have an empty space, to be fully recovery or not.
you're gonna talk about these the row spans, right, which are the intersection of these things, right? And those being empty sort of require some probabilistic guarantees of this.
It's possible. I agree now that you tell. I feel that
feel like it
perhaps
should be-
M is big, or
Yeah,
I
one
agree
of them
with
has
you.
to go to infinity for these things to kick
Yeah,
in,
yeah,
right?
yeah. I agree. I have to check a bit more carefully, but just wanted to say that. So now I've just presented what we are doing on this and what are our future extension. We are really interesting to go in nonlinear. The way of doing that, most likely we will first linearize because we don't know what else can be done and to have a nice theory. And the goal is to kind of look at this robust invariant manifold, and we want also to use this theory for neural network and check actually how robust are neural network and what are the direction and so on. So this could be, and perhaps the E will be in X star. So imagine that you corrupt some of your input, what's happening to the neural network, and what is robust and what is not robust. So we are hoping that this theory can be extended to this case. Then, of course, we would like to go to some kind of noisy regime to really be able to tackle inverse problem. But this requires a lot of work to say something interesting. And then, of course, we also are currently looking at, right now we have looked at L0 recovery, but a lot of people in compressed sensing also are just asking themselves, imagine that you're solving this optimization problem. When do you have a unique solution? So this is also, again, all the RIP condition and null space property and so on. And we can ask the same questions there, is when are we able to can we recover necessary and sufficient condition to recover U of X star?
Yes, I think for this problem, maybe you can do even worse, right?
Yeah.
2 instead of 2Q is probably larger. Right?
Most likely because L1 is relaxing. Yeah.
Because that would be really interesting, but this is solvable problem.
Exactly. You know, L0 is actually solvable.
No, I agree. For the small
People, no, not even small. People have, it's just that mathematically you don't have good guarantee, but all the heuristics that are on the market are actually working pretty well. You know, they do greedy, basically greedy thresholding and so on. It's actually working, and this is what's implemented. But you cannot say anything theoretically. Okay? And then, and then that's it. That's it. And about the paper, this is something else that I will talk about later. So this is the papers that have been submitted, and we are waiting for the reply. And there will be soon a journal version online. And we have also other work on this where we tackle a certain type of noise with Gohan, and where we more ask how to do algorithm to exactly recover the X star with some kind of decreasing noise. Okay? So these are all these algorithms there, and we also ask this, in this case, and I think Gohan have already presented this work at this seminar, when our algorithms are converging to UX also. Okay? And a bit of advertisement. I don't know if there is master student here. If not, I will still tell. We are opening a position in online machine learning algorithm for optimal cyber defense in large network. And so if you are interested, you can just contact Ezekiel or myself. And it's again math for cybersecurity, but it's this kind of math also. Okay. That's it.
Let's all thank the speaker. Thank you, Professor Alex, for agreeing to deliver a talk and giving such a wonderful talk. And are there any questions from the audience?
Initially, you mentioned that L1 norm or L2 norm of E that you're mentioning is unbounded.
No, I'm saying norm of 0 is unbounded. No, what are you saying?
No,
Yes,
the error, like you're just considering the L0 norm is less than or equal to Q.
Yeah.
But you mentioned that like L1, we are not keeping any bounds on L1 or L2 norm. But like if you're looking at some measurements, and if you're saying for some of the entries the value is very high, if you just look at the so if they are very high, then like can't you just know, okay, these are the sets that I need to remove, or these are the entries that I need to remove, and then you would know, like, for example, if let's say this y1, y2, y3 are very small, and whereas because of the malicious adversary you have maybe y4 and y5 to be like 1000, then you would know that your attacker has access to the sensor 4 and 5, then you can just remove those measurements. So wouldn't it be natural to keep the L2 norm or L1 norm bounds on?
So in practice, this is what people do. You look at your measurements, you are an expert, and you look at outliers, and fair enough. So first of all, we wanted a systematic theory to do that. The moment you put a bound on, it's much easier to say, I have Q sensors that fail, but I don't know how. Than to say that my norm is bounded in terms of amplitude, right? So how do you define this threshold? You see, and in practice, what you are just saying is that, yes, I see that it's really high, so I can just remove it. Actually, it's really, really hard to do in practice because you really need to know your system, to project in the right space, and to check the outlier. And because I agree that it's not actually a bad assumption to say, if it's too high, I remove. But defining this notion of what is too high is actually a part of your algorithm.
Yeah.
So
finding the threshold is important.
Yeah, and but in hypothesis testing and so on, this is actually what they do. Actually, after a certain threshold, I decide this assumption, so we wanted to start with as low assumption as possible to be able to say what can be done. And then we are trying to complexify. And we have also another PhD student and other colleagues that actually look at practical problems. And of course, this theory cannot be applied to complex data for now. This is why instead of adding this kind of other noise that you are suggesting, we are looking for nonlinear.
So one of the last question is that in your last slide regarding PhD positions, you mentioned for cyber physical system. Now it's not just like y equal to cx plus e. Now because of the dynamics, now the e will not just have some sparsity, it will have some structured sparsity into it.
If you are interested in that, just talk to me. It's fancy word to get money. Huh? So I agree. You can, but you know, the question in all this problem is just to, right now it's a theoretical work. The question in all this problem is what are the minimal assumptions that you can add where you can say something and that are not completely crazy. Of course, I can even say that A is corrupted. I can say X also belongs to something. I can add thousands of them. But we have to be careful with which one we add. It's part of the job, actually.
Any more questions? On. I hope Professor has addressed all your queries. So, and if you want to connect with Professor, please do so by having refreshments at our coffee hut. Thank you all and have a great evening.
Thank you.